Welcome on and all to the Math Magic Show. Let's be serious now, this is mathematics. So in this one we're going to do is go through a fairly rigorous example of finding what values of x should have, so that, for example, the difference between a function and its limit is within some specified range, for example, like, less than a tenth, or whatever number you want, but I'm going to show it for the case of 1/10, but it could be 1/20th, 1/50th, whatever you want. Same logic would apply, okay? But the numbers would be a bit different. So to work this out, let's begin with this one. I'm going to say the following first. That I have here 2x plus 1, that's my function. And imagine that when I form the limit, I have the limit as x approaches here 1 of 2x plus 1. Well, you can find that one by direct substitution. That would just be 2 times 1 plus 1, which is 3. Once you have that in place, imagine that what you want is the difference between the function value and the limit to be, say, 1/10. So to do that, you're going to use the following. You're going to say absolute value and then f of x minus L is less than 1/10. Why am I writing this? Why do we write anything in mathematics? It's because we have found that it's useful, okay? We're just looking for basically the absolute value of a difference between two quantities to be less than some number that we want, like 1/10, or it could be 100th, okay? Just a number. So this part right here, this is made up. It could be a 10th, a 20th, and so on, okay? So the next stage, the way to proceed here is as follows. You want to replace f of x with its definition, and you want to replace L with its value as we have found it here. So I would say that I have 2x plus 1 minus L, which is 3, and this should be less than 1/10. Now from here, take a look. It's going to be 2x minus 2 less than 1/10. And something magical, so to speak, is happening, which is that we're getting close to having an x minus 1 within the bars. Why would we want that? Because the x minus 1 measures how far you are from the 1 on the x-axis. So if you think about this very carefully, in this particular function, right, when you write f of x minus L, you're beginning on the y-axis, essentially, because you're looking for the difference between the function value and the limit of the function. But when you manipulate this, it brings you back down to the x-axis. That is the essence here in this particular example. And of course, this looks kind of awful here, so I need to fix that. Okay, one must take pride in one's writing. So then I'm going to factor the 2 from each term inside the bars. So it's going to be 2 and then x minus 1 less than 1/10. And let's stop right here. This is something we should observe. This one right here that says x approaches 1, it's also now right here. You see that? That's what we want. So now I'm going to say 2 on the outside, and then x minus 1 is less than 1/10. This is working out quite well, because now the x minus 1 in absolute value bars, that is literally measuring the distance between the particular value of x and 1, and the same one is right here. It's this one and then this one right here, the one that you're approaching the x-axis. And the x would be like a value perhaps slightly to the right of the x, or a value slightly to the left of the x. Let's finish this up. Our next step here would be to divide through by 2. So I would have absolute value x minus 1 is less than 1/20th. So what is this saying? Well, this might still seem a little bit cryptic. Let me just break it up. Because we have an absolute value inequality, you put it into two separate pieces. So it looks like this. Negative 1/20th is less than x minus 1, which is less than 1/20th. Let's finish this up. So I'm going to add 1 everywhere. So plus 1, and then plus 1. Tally up the results straight down. Of course, these two will cancel off in the middle. Okay, and I'm going to have the following now. Negative 1/20th plus 1, when you work that out, that's 0.95, which is less than x, which is less than 1.05. So what is it that we have found here? Let's think about this for a second, right? We began with f of x minus L less than 1/10, a statement about what's happening in the y-axis. And through the sequence of manipulations, we ended up with this, which talks about the x-axis. And it worked out so beautifully in this case. Let me give you a visual interpretation of what this means, it's this line right here, so that we can understand why we have done this, and not just that we have done it. That's nice, but that's not too interesting after a while. So what I'm going to do is draw a picture. Okay, so that will be my y-axis, this will be my x-axis essentially. Let's draw the function in there also. So remember, the function is 2x plus 1. That means a y-intercept of 1 and a slope of 2. Don't forget that basic fact. So slope, let's see, 2 and y-intercept 1. So this is, imagine, 1 right here. And a slope of 2, well, If two grid lines, or two little boxes represent a 1, and a slope of 2 would be 4 boxes. So I'm going to say it's 1 this way, and then 1, and then 2, which is really 4 boxes, and then you connect that with a straight line to the best of your ability, kind of this way. Okay, just like that. And what we have found is the following. We have this 0.95 and then 1.05. So if this over here is 1, say this is 1 in this position, that's 1 on the x-axis. So what this inequality says is the following, that if you are between here, which is 0.95, and say here, I'm exaggerating a little bit so we can visualize things properly. So if you are between 0.95 and then 1. What did I find there? I think it was 1.05. If you choose any value of x from here, from this narrow range of values, then the output that you get on the y-axis will be less than 1/10 from the limit of the function. That's the key idea here. I hope you're truly getting that. So we can visualize that a little better than this. Take a look. Imagine that over here, I choose some value, intermediate value. Imagine this is 1.01. 1.01 fits between 0.95 and 1.05, okay? Which means that if I plug 1.01 into the function, the output, let me mark that. I'm going to erase the slope triangle just so it's not in the way anymore. Okay, so I've erased the slope triangle and I'm plugging 1.01 into the function. Well, let's see here. When I do that, I have to be really careful. So let's see, that would be roughly like that. That would go in, which means this would be the output right here. See that? Now let's ask ourselves a question. Every 2 spaces is a 1. So for example, like, this is a 1, this is a 2, and then this is a 3. Okay, so this is 1, this is 2, and this is 3. And notice that the output on the vertical axis in this position right here is very close to the 3. And specifically, because I chose a value like 1.01 from the x-axis, it guarantees that the output on the y-axis is less than 1/10 from the limits. So in other words, it means this. Take a look. This is really going to wrap up the whole show, so to speak. I will have 2 evaluated at 1.01. So then that was, I believe, plus 1. Okay, that's the value of the function. In other words, where the arrow hits the y-axis. So that's 2.02 plus 1, which is 3.02. And if you take away from that the value of the limit, which is right here, that's the limit, L. So this is 3.02 right here. Okay, the limit is 3, so there's a bit of a space in this position. That space is what we are about to measure. Take a look. It's going to be 3.02 minus 3.00, which is 0.02. And 0.02 is less than 1/10. So in other words, 0.02 is less than 1/10. In case you've forgotten how to compare these kinds of things, perhaps it's been a while, I'm not sure, you might just write this as 2 over 100 less than, and 1/10 when you multiply bottom and top by 10 would give you 10 over 100. So in other words, this shows something important, which is that this number is smaller than that number. And this is guaranteed by the fact that we went through all of this work and we see that the number on the bottom of 1.01 right here, this number, lies within this narrow range between 0.95 and 1.05. But remember, our inequality was strictly less than, which means that these numbers themselves would not be included, okay? Those would be like, for example, holes if you wanted to mark them, to be very precise. So any number that you choose from here to here, you plug it into the function, it guarantees that the output on the vertical is less than 1/10, which is this right here. Let me zoom out so you can see all of our work from beginning to end. I love these kinds of exercises that stretch our imagination. As you can see, it's kind of small when you look at it from this perspective, but I wanted to kind of show you some of these important things. This is all of our work, mathematically speaking, that is. And then let me also zoom in on the graph one last time, so you can see what we did on the graph, and the graph looks like that. Thank you so much for watching. Please leave a like and subscribe. I'll see you in another video.